So welcome once again, buongiorno, bonjour and guten morgen to everybody. And then there we are. We continue with what we have been doing. In a couple of minutes, let me recap very briefly what we were talking for a continuity. Okay. So you see, we considered the Polyakov Lagrangian. This was minus t by 2 and del alpha x mu. So this was the conformally gauge fixed Polyakov. Now let me put Lagrangian. Because I have written that Lagrangian. If you want to write the xn is, and you integrate over into sigma. So this is what we obtained after the gauge fixing, after the conformal gauge fixing, where you assume as alpha beta to be proportional to g alpha beta or as alpha beta proportional to g alpha beta. Correct? And we put the proportionality constant to be equal to 1. And now we have seen we also need to know in the first place, yes, so what we were doing with this action, we used the variational principle and we derived the equation of motion x mu, this equals to 0. This is del alpha, the D'Alembert, and so you could write it either in the x prime square and d2 sigma, and here you write down this equation of motion x equal to 0. This implies equals to 0, or you write it down the Lagrangian, that would be minus t by 2, and this is del plus x mu del let me just give the last results. So this is minus t by 2 into minus 2 into minus 2 into del plus x mu del minus x mu. Okay, so we can write it down in terms of the light front coordinates. So this is the action. For that, let me briefly briefly write down sigma plus minus is tau plus minus sigma, and so tau is half sigma plus sigma minus, and sigma is 1/2 sigma plus minus sigma minus, and del plus minus, del plus is del sigma plus, this is 1/2 del tau plus del sigma, and del minus is, this is 1/2. So back and forth wherever we like, whenever we like, we can go from instant form to light form and so on. And So we need to remember that x plus is minus 2 x minus and del plus minus is minus 2 del minus plus. Okay, and here eta alpha beta is minus 1/2 minus 1/2 0, and this is 0 minus 2 0 minus 2. So the metric in the light front coordinates. Now what we did last time, we considered the action conformally gauge fixed Fourier approach action, and we varied and we obtained this part, and we obtained the boundary terms which were of the type x mu x prime, let me put this times delta. This is what we did last time. And so what we want is, we are interested only in retaining this so that our action of the theory remains Lorentz invariant, a Lorentz scalar, and for that these things, they must be identically 0. They of course do not vanish on their own, because these boundary conditions are on the spatial dimension sigma. Whatever boundary terms we had, plus we had some boundary terms, they were on the time boundaries. And these terms, they vanish on their own, because here delta x mu on time boundaries is identically 0 at minus and plus infinity at the time boundary, just like field theory. In field theory, all the fields are supposed to vanish at the infinite space-time boundaries. So these terms vanish, they drop out. They don't drop out on their own. So we make two choices. Delta x mu equal to 0 or x mu dot equal to 0. This is one and the same thing, because the boundaries remain fixed with time. Anywhere the string can fluctuate, okay, but this end remains fixed, okay. So we call them Dirichlet boundary conditions. In the other case, x prime equal to, they are the ones that, so the end point at x mu at sigma equal to 0, at sigma equal to 5, the ends of the string can fluctuate, okay. They need not remain at the same point. In addition to this, they can fluctuate as well, but the end points are no longer fixed. So x prime mu equal to 0, and these we call as Neumann boundary conditions. Of course, we can have Neumann at both ends, Dirichlet at both ends, or the mixed boundary conditions, ND/Dn. Okay, but we have to watch out for them, because as we will see today, today's lecture is basically a recap of some of the very important issues that are involved in the so-called solution of this field equation. We would solve it in the right front coordinates. We would split it into two parts, the left moving and right moving parts. We would expand them into the Fourier modes, and then we will make use of these boundary conditions and so on to study these Fourier modes and express then everything in terms of the Fourier modes, right? And eventually derive the mass spectrum of the theory. Now, in the next lecture, so far until today's, we are not going to consider compactification of any extra dimensions in the theory. But in the next lecture, we would explicitly consider compactification of one of the dimensions, spatial dimensions. We will consider x25 and compactify it along a circle. Okay, so Kulshreshtha kind of idea, Kulshreshtha theory is kind of idea. And in that case, comparative to today, what you will see that the mass spectrum would change when we compactify one of the dimensions or all of the extra dimensions. Our theory has extra dimensions. In bosonic, it's 26. So 26 minus 4 are the extra dimensions. In fermionic, in the superstring theory, 10 is the number of dimensions. So 10 minus 4, we live in the 4-dimensional world. So 6 dimensions are extra dimensions. And we would take an explicit example of one particular dimension and compactify it, then see. So relatively, we would see what happens here in the present case and what happens when we compactify a particular dimension. Okay? And then in the remaining lectures, again we would study the things comparative to this. So here what is happening, this x mu is bosonic. X mu is bosonic. So here the Fourier modes, the coefficients of these exponential terms, okay, or the annihilation creation operators involved in the expansion of x mu, they would be bosonic and they would obey Bose-Einstein statistics and the corresponding commutation relations. However, when you write down the superstring theory, then again you would have some equation of motion and so you would have some equation of motion. It would be the same, and this would give me, so that would be my field equation. Well, sorry, psi mu. This would be my fermionic field, and we would take it to be Majorana spinner, which is real. Here also we had the advantage that this x mu is real. Okay, it's a real scalar field on the two-dimensional bird seed. This is also a field on the two-dimensional bird seed. It's a function of the sigma alpha, sigma 0, sigma 1, or sigma plus, sigma minus. And here, no, I am sorry, it cannot be. It is either this or these are Dirac equations. What I wrote down was this. Okay, so they are the Dirac equations. Okay, I am sorry. What I had written down was the expression for the Lagrangian, which was del plus, what is this? Oh, that was also wrong. Del plus x mu, del minus x mu. Okay. So what I had written, that was incorrect. This is correct. So we will have these equations. These will be Dirac equations. Okay. And let me not even write this actually. It may be technically incorrect, but these are technically correct. Okay. Because Dirac equations are first order equations. Let me not go into that question. So for the superstring theory, we would have Dirac equations and their solutions. So we would make expansions for psi mu, and they would involve also Fourier modes, and those Fourier modes would be fermionic in nature, and they would obey Fermi-Dirac statistics and the corresponding anti-commutation relations. All right. So it's comparative. That is the purpose of recapping some of the basics related to the bosonic string theory. Okay, because we want to make a comparative study, and we would leave out many derivations. For that, I would refer to the earlier lectures. Okay, they are also on the net. So All right. So I think we now come back to this. As you can see, is Klein-Gaussian equation for the massless fields. These are H mu are the massless scalar fields, and so this is expected as to be this equation. So what we do now is we want to, making use of the light front coordinates, we would like to split this into two parts. The x mu tau sigma, I could write it as x mu L, which is a function of plus x mu R, which is a, so this sigma plus is tau plus sigma, and sigma minus is tau minus. So this is in general for any wave equation. We can split the solution of the wave equation into two parts consisting of two waves, one moving to the left, one moving to the right, and for short they are called left movers and right movers. The point is one of them depends only on sigma plus and one of them depends only on sigma minus. Okay? So sigma minus is tau minus sigma, so it's a right mover. This is tau plus sigma, so it's a left mover. And we would use the convention that here, for this I would use alpha mu k. For this I would use beta mu k. If I make a mistake, you could tell me, catch me, and so that I give the direction. So this is one thing that I can split my solution into left movers and right movers. Second step is, in general, for any partial differential equations from the theory of partial differential equations, we know that we can make Fourier expansions for these solutions. Okay, and the simplest Fourier expansions are the plane wave expansions. You can find different other kinds involving cylindrical waves, spherical waves, and whatever you like, but the simplest is the plane wave expansion. So here let me write down these two expressions. X mu L is 1/2 x mu L plus 1/2 ls square sigma plus, or let me better write here tau plus sigma for a different region so that you can do mental calculation. PL mu plus k not equal to 0, but k going from minus infinity to plus infinity, 1 by k times alpha mu k times e to the power minus I k, let me write tau plus sigma, but we remind ourselves that this is also sigma plus, and x mu r is 1/2 x mu r plus tau minus sigma p r mu plus iota l s y is equal to 2 summation over k in the same manner, k not equal to 0, but k goes from minus infinity to 1 by k, and here I write beta mu k e to the power minus I k tau minus. Okay, so the total solution is of course x mu is equal to x mu n plus x mu r. Okay, x mu n plus x mu r. Correct? So this total solution would be, I would not write down fully, but 1/2 of x mu n plus x mu r plus 1/2 ls square into sum of these two terms, okay, plus the mode. So without writing these expressions for them, I leave it. Very soon these various conditions on our field x mu, capital X mu, would relate some of these things like this, and P R mu and P L mu and so on. Okay. If we assume P L mu to be equal to P R mu, then I could of course write it down immediately that if this is equal to this, then this term would drop out and I would have a 2 twice tau into P mu. Then let me not write here L or R or L or R. Here I am assuming this to be equal to this, but it may or may not be equal to. So therefore I just leave it open. Okay, be some of these two terms. That's enough. Now physically, what is the meaning of all this? This object, sum of these two terms, this represents the center of mass coordinate of the string. Center of mass coordinate of the string, and this sum of these two, whatever it is, would represent center of mass momentum of the string. Actually, if you solve an equation of the type x double dot mu equal to 0, just this, it would imply u x mu equal to some x mu plus p mu tau. Okay, just equation of motion of a free particle. So you integrate it twice. You integrate it first, you get p mu. You integrate it second time, you get p mu into tau plus another constant. So x mu, p mu are essentially constants of integrations here, but physically they represent the center of mass coordinate and center of mass momentum of the string. So the space time, within the space time, the string moves around with this sum of these two terms, this plus this and this plus this. So this part, center of mass coordinate and center of mass momentum, sum of these two terms. So string moves around in the space time with this, and it fluctuates with the second part, which represents the oscillation. So it oscillates via the second part, sum of these two, and it moves around with the sum of these two. All right? Okay. So, and just to give you an idea that this kind of a thing, so for a string, I mean this is just a demonstration for a free particle. So that this x mu, what have I done? I have made a mistake. I should not have written capital X. This must be small x. These are small x, which I am saying coordinates. Okay. These are the string coordinates. These are our string fields. They are the fields that correspond to the one-dimensional object called string. Okay. And we have not yet considered whether we are going into open or closed string. We now look at it, and by looking at them, we can impose a few things. So let me just remove this part. Now, without going into mathematical derivations of some of these things, it may be enough to recap that, for example, here this k is the wave number of the wave vector. Okay, here this k is the wave number of the wave vector. It need not be an integer, but we will see whatever boundary conditions tell us. Okay, so in the now, for example, we go to open strings with Neumann boundary conditions. Neumann boundary conditions at both the ends, which means at sigma equal to 0 and at sigma equal to pi. Okay. So, and what is the condition? Neumann conditions. They tell us the boundary conditions. The x prime mu equal to 0. So what you do is you consider del sigma x mu equals to 0. Okay, the space derivative of x mu. Space derivative of x mu has to vanish at sigma equal to 0 and at sigma equal to 1. It be imposed at both the ends, the same n. Okay, so I would be right now considering only n and dt, but you can also consider nd and dn. Okay, so you take x mu, take its sigma derivative and equate it to 0. And this would give me, let me first do it at sigma equal to 0, then this would be del sigma x mu l at sigma equal to 0 plus, no problems, this is del sigma f mu r at sigma equals to 0. And if I do that, then what I find is that 0 equals to from here, coming from outside. Oh, okay, fine. I am happy. I thought something was wrong with one of these cameras, but it's okay. If it's coming from there, that's fine. So, all right. So what are we doing? We consider x mu, which is the sum of x mu l and x mu r. And we want to take the space derivative of x mu, and we want to make it at sigma equals to 0. Okay, so we are applying the Neumann boundary condition at one end, at sigma equals to 0. And if you do that, in this I have omitted the intermediate steps, which are trivial, and they are step by step also given in my earlier lectures. I noticed. So what we get is this and this. So what happens, that both the terms will have to vanish separately. if the left hand side is 0. So I would get PL mu equal to PR mu, and I would get alpha K mu equal to beta mu. This would be the outcome. So outcome is X no PL mu equal to PR mu. And the other outcome is alpha mu K is beta mu. This is the outcome. Okay. Now, when you apply this condition at this point, I have written at sigma equals to 0. Okay, right now I am doing it at sigma equal to 0. Now, so can I, maybe I need to remove this part. Alright. Now, I would like it to vanish at sigma equals to pi. At sigma equals to pi, and we again skip the mathematical details, and when you demand this thing to vanish, the space derivative of x mu to vanish at sigma equals to pi, then we arrive at k equal to n equal to integer. That is the only outcome. So the other outcome is that k equals to maybe n or whatever, but k is an integer. Okay, that is the outcome. If we apply the Neumann boundary condition at the other end also, at sigma equal to pi also, if we apply, we get this. And you see, just a remark, in fact, PL mu equal to PR mu always holds for a non-compactified dimension. So if all your dimensions are non-compactified, this would always hold. Okay, PL mu equal to PR mu. Also actually for open strings, also for closed strings. We will go step by step. Just to recap the main results, what are we doing, what are we having. Okay, skipping some of the details which otherwise it will go on into several lectures. So this is now if you apply the if you consider the open string with DD boundary, but at both ends DD, okay, and then what you would find, you would like this to vanish, or you would like this also implies, okay, so this is also built into that, okay, so x mu does not change with time. That is our boundary condition. And in this case, what you will find is, I mentioned you the result. Here, what is the result? The result is for that PL mu is equal to minus PR mu. This is one outcome, and alpha K mu is minus beta mu K, and when you apply it at the other end, so these are the two net outcomes. That at one end you get this and this, and by applying this Dirichlet boundary condition, you get k equal to an integer. Now, so what happens here? This is in conflict with V mu L for a non-compactified non-compactified dimension. You see, no, PL mu equal to minus PR mu is in conflict with the case for the non-compactified dimensions. For non-compactified dimensions, PL mu is always equal to PR mu. So this has to be equal to this and this has to be minus equal to this. Then the only alternative left with us is both of them should be 0. So PL mu is 0, PR mu is 0. Finished. So if that happens, then this is also equal to plus of that, minus of that. Okay. So we are safe. Alright. And another condition we get is K is an integer. Fine. That is also fine. So one conceptual outcome is that for open strings we can just survive by dealing with one kind of modes, because other one is just a minus of that. Okay. That too not always. Here it's just identically the same for Neumann boundary conditions. For Dirichlet boundary conditions, this is equal to minus of that. So what we are going to do with these modes ultimately is to construct the mass spectrum of the theory. Okay. So if we know one, we also know the other. So it's enough to talk in terms of one of the modes. Alright? The other mode is essentially the same. Okay? And if we consider the closed strings, then for closed strings also it follows that this holds true, but this does not hold true. Okay. So for a closed string, this is right now these are the results for the open string with Neumann boundary conditions, and these are the results of the and for the closed strings, P mu L is P mu R is fine, and alpha mu K is not equal to beta mu K, but K is still an integer. But K is still an integer. So no problem. When we talk about closed strings, we consider both the modes, alpha and beta, for everything. So like if you want to write down commutation relations for them, you write down for alphas as well as for betas. In open string, it's enough to write for one and the other one follows. Okay? Good. So this is what is the summary of all this. And yes, here let me explain this. Let me come back to these Fourier modes or these expansions, Fourier expansions of these things. Now we know that K is always going to be an integer. I must make a remark here that these three cases, open string with Neumann, Dirichlet, K is an integer. Closed string, it's an integer. But if you consider Neumann, Dirichlet, Neumann, K is not an integer. Okay, but I would not be considering these details, but it's very trivial. You apply those conditions at one end, at sigma equal to 0, you apply x dot equal to 0, for example. At the other end, you apply x prime equal to 0 and derive the consequences. You will find that this should be half integer. Okay, K should be half integer. It's enough to know, remind ourselves that, okay, but otherwise this is going to be an integer. Okay, and when it is going to be an integer, k not equal to 0. So k we could replace maybe here by, let us say now, n or m. Just to remind ourselves that this we are dealing with an integer, okay, but still n not equal to 0. So what happens here, n, but otherwise n goes from minus infinity to plus infinity. So what does it mean? It means for my n I would have minus infinity, minus 2, minus 1, minus 3, okay, and then plus 1, plus 2, plus 3, plus 1. Okay, so the sum goes from here to here, also from here to here, but here at the moment I am excluding the term n equals to 0, but I would include it shortly, and so at some places you can include it. So what actually happens, that n equal to 0 corresponds to the 0th order frequency mode, or in short it's called a 0 mode. Okay, the 0 mode, which is the 0th order frequency mode. Okay, so for that I would have let me not make mistakes, so I come back to my pages. So alpha 0 mu, this factor actually could also be written in terms of alpha prime. Okay, alpha prime, the Raja is slow, it's related to this length string length. So this Pl mu and beta 0 mu equal to Ls by square root of 2 P mu r. Okay, so these are the two terms. So if I would like, at some places I would include them also in this manner, or I keep them out. Okay, alpha 0 and beta 0, and for that reason I have written n not equal to 0. So n not equal to 0 term is not there, but otherwise you sum it from minus infinity to minus 1 and plus 1 to plus infinity. Okay, all right. So now we can think of a few more things on this, but before we do that, I come back to what we have. This I think now more or less we can, if you like, we can remove these expressions, okay, because we now know fairly well all these things. Okay, okay, so now, one thing, what we have studied in the past, in general, for the polyomino action, we have proved that T alpha beta is equal to 0, correct? In general, T alpha beta has to be 0. So what does it mean? All its components like T plus plus here or here, as you like, T plus plus, you can relate them, okay? You can take one sign up or down as you like with the help of that Lightfront metric. Okay, so T plus plus, T plus minus, T minus plus, T minus minus. Okay, that is my T alpha beta. Okay, in these two dimensional worksheet. And then we have also proved that this is 0 and this is 0, and this we have non-vanishing values for them. And what are they? Let me avoid making mistakes. So I write T plus plus is del plus x mu, maybe whole square, or del plus x mu, del plus x mu, and T minus minus is, so this is del minus x mu, and Matthias, I have just said that we have already proved that T alpha beta is 0, correct? In general, for the Polyakov action, and therefore all its components also have to vanish. And we have seen T plus minus is 0 and T minus plus is 0. So the point is, what is the physical spatial meaning or physical conceptual meaning of these objects called T plus plus and T minus minus? T plus plus in my notations I obtain as del plus x mu whole square, okay, and T minus minus I obtain as del minus x mu whole square. So T plus plus vanishes on its own, T minus minus vanishes on its own. These are called as Virasoro constraints of the theory, and at the moment they are at the classical level. When I am talking in terms of x mu, then they are the classical Virasoro constraints. Okay. Now, but I know my x mu, I can make a Fock space decomposition for x mu. The Fourier, I can expand it in Fourier modes. Those Fourier modes alpha mu k and beta mu k, or alpha mu and beta mu n, they are quantum mechanical operators. They are the annihilation and creation operators. Okay, I mean one and its dagger, Hermitian adjoint. Okay, so we would like to understand them. These are the Virasoro constraints. Okay, at the classical level, we would like to express them at the quantum level. And when we do that, as we know that the expansions for x mu involve these Fourier modes alpha mu and beta mu, which are quantum mechanical operators. When we do that, we construct a new object called as the Lm or Lm bar. They are called as the Virasoro operators. Okay, and let me write them down, and then we know what they are. Okay, so let me just remove only this one, but let me retain them. Okay, so now let us take del plus x mu is del over del x of del sigma plus. Okay, now this is del over del sigma plus of x mu L, which is a function of sigma plus, plus x mu R, which is a function of sigma minus, and this is del over del sigma plus of x mu L, which is a function of sigma plus. The other guy gives me 0. Okay. When I take partial derivative of x mu with respect to this variable, this gives me 0, but this term survives. And I know the Fourier expansion for x mu L. Okay, that is what we already wrote down there. So what we can have is of of x mu L sigma plus. Okay, just this. And so I assume that we write down the expansion. So this would give me 0 plus ls square by 2 p mu L plus iota ls by square root of 2 sigma k not equal to 0, or let me write now n not equal to 0, 1 by n times, I am differentiating this, so I have minus iota n times alpha mu n e to the power minus n sigma plus. Now I need to change. So is this okay? So you see, minus I into plus I this guy and this guy, that gives me plus 1. This guy goes away with this guy, right? So my life is now much simpler, and it is I can write this, and so this is equal to now ls by square root of 2 I have defined in the first place PL mu ls by square root of 2 times P mu L is, why is this ls square here? Is this ls square here? Okay, so this I can write, this is alpha 0 mu, so 0 plus ls by square root of 2 I can separate, and alpha 0 mu plus ls by square root of 2 not equal to 0. This goes, alpha mu and e to the power minus I and sigma plus. Correct? So what I am doing right now is I am trying to construct, let me have just this expression here and this result here. This is del plus x mu is this. Okay. Now I